Hi, hello everyone. First of all, thanks for being here in my YouTube channel. Let's talk about three-phase induction motor slip and its significance. And also we'll derive rotor induced frequency. Before getting into the topic, we'll see how does three-phase induction motor works. I'll be giving three-phase supply over here because three-phase induction motor, right? Three-phase voltage. Due to voltage, current will flow through the three-phase coil or three-phase winding in the stator. When coil carries a current, what happens? Produces flux, right? So the produced flux rotates at a speed of ns is equal to 120 f by p, right? And also called as a synchronous speed or rotating magnetic field speed. This 120 is the phase angle. Placing of this stator conductor or stator coil 120 degree apart each other, and f is the supply frequency, p is the number of poles in the stator. And next is a rotor. If suppose rotor conductor cuts this rotating magnetic field, what happens? Induces a current, right? According to Faraday's laws of electromagnetic induction, conductor carries a current placed in a magnetic field, experience a force, right? So the conductor starts rotating, mechanical output, right? So this is the working of a three-phase induction motor, right? We'll get into the syllabus. Slip and significance. Slip is defined as it is a ratio of slip speed to the synchronous speed. Okay. Already we discussed synchronous speed, that rotating magnetic field speed rotates at ns is equal to 120 f by p. If you give power supply to the stator winding, right? That is a synchronous speed. Next, slip speed, right? So slip speed is the difference between this rotating magnetic field speed or synchronous speed and this rotor actual speed. I mean mechanical output of the rotor speed. So slip speed is the difference between synchronous speed minus rotor speed or actual speed. Okay, this is mechanical output. This one is rotating magnetic field speed. That is ns minus nr, right? That is slip speed. I substitute this synchronous speed and the slip speed over here. So s is equal to slip speed divided by synchronous speed, right? Slip speed is ns minus nr. Ns minus nr divided by ns, right? So slip always represent in percentage, unitless. So ns minus nr divided by ns. Keep it in your mind. If you want rotor actual speed from this equation, so I'll just multiply over here. Ns into s is equal to ns minus nr. So if you want rotor actual speed, so nr is equal to ns minus ns into s, right? So nr is equal to ns. I'll take common outside 1 minus s, right? This is the equation of rotor actual speed, right? So finally, rotor actual speed is equal to ns into 1 minus s, right? So we'll see the significance of slip. If slip is equal to 0, what happens? Rotor actual speed, I mean rotor speed, nr is equal to ns into 1 minus 0. We will get nr is equal to ns. Motor will not rotate because interlocking will occur, or rotor conductor will not induce any EMF because the jam condition. Okay, so motor will not rotate or interlocking. Okay, interlocking, no rotation. If s is equal to 1, what happens? nr is equal to ns into 1 minus 1. You will get nr is equal to rotor actual speed is equal to 0. So start condition or stationary condition. Okay, motor will not be rotating when s is equal to 1. Always slip range 0 to 5% for good motor. Okay, anybody notice this diagram? Because this rotation of rotating magnetic field also same speed and this rotor also same speed. So this condition is applicable, right? So this diagram is wrong. It should be less than the synchronous speed. I mean this rotor rotation must be less than this synchronous speed. Then only the induction motor will work. I'll show how exactly at the end of the video, right? You can draw this diagram. Torque slip characteristics. Slip is equal to 0, start condition. Slip is greater than 0, less than 1. You can say motoring action, motor. And slip is less than 0, generator. And slip is greater than one braking reason. See here slip is start condition. Here slip is greater than 0, less than 1 motor, and slip is less than 0 generator. Okay, as you can see the diagram, perfect diagram for induction motor. See here rotating magnetic field is faster than this rotor speed, right? So for motoring, ns is always greater than nr. Keep it in your mind. This one is motor, and if it is ns is less than nr, you can say generator, induction generator. If it is nr is equal to 0, start condition. Okay, I mean rest position or stationary position. nr is equal to ns, blocking condition or interlocking condition, jam condition. Rotor conductor will not produce any induced EMF because block or interlock or jam condition. Okay, so this you can write in your significance also, right? We'll derive rotor induced frequency now. Initially, rotor is in rest position or stationary position. What happens? Supply if you give, so that supply frequency is equal to rotor frequency. If suppose rotor start rotates, induces a current, right? So that induced current frequency is directly proportional to slip speed frequency. So ns minus nr is equal to slip speed, that is 120 fr divided by p. This one I'll take equation number 1. Okay. So what about synchronous speed or rotating magnetic field speed? Ns is equal to 120 f by p, right? Equation number 2. Take equation number 1 divided by 2, you will get ns minus nr divided by ns is equal to 120 fr by p divided by 120 f by p. This p get cancelled, 120 get cancelled. ns minus nr by ns is what? Slip, right? Slip is equal to fr divided by f. So if you want rotor frequency, fr is equal to s into f, right? So rotor frequency is equal to s into f. This is a rotor induced frequency in the conductor. Okay, so just to consider, this is a stator and then this one is a rotor. Here there is a conductor present. When a conductor cuts this rotating magnetic field, what happens? Induces a current, right? This will induce like this current. So this frequency is called as fr. So is equal to s into f. Okay, it depends upon supply frequency also and slip also. Okay.